So wave times, or what we call timing diagrams, are a diagram that represents the changes of the inputs and the outputs of any Boolean expression or logic circuit over time. So over time, we could change the values of A and B by, say, turning a switch or pressing a button. And then the output X is going to change instantly as these buttons get changed. So all we're doing in a timing diagram is we're saying, well, let's let this be an axis that is called time. And this curve that I've just shown, I have an input called A, and it started at 0. So let's say in the real world, that's somebody, this is a button, let's say it's a push button. Then when time started, nobody had pressed the button. And then at this time, the button got pressed. So then the input of A went to 1. This is a 1. It was previously at 0. Now somebody pressed and held this button for a period of time, and then they let go of the button and the signal went back to 0, which is 0 volts. Then at this time, you see this is a time, this is a time, and this is a time. So this is, say, T1, and this could be T2, and this could be T3. And then at T3, a person pressed this button again, and now it's 1, or high voltage signal, right? 0.7 volts or 1 volt, however the circuit is set up. And then the person let go of the button again at time T4, and the signal went back down to 0. Similarly, there was another button called B, and that person first didn't press the button, and then at this time they pressed the button and it went and it held as a signal 1 as they keep holding the button. Then they let go of it, it goes down to 0. Oops. And it goes down to 0 at this time. And then they wanted to press the button again, so they went, it turned up to a 1 here. So in a timing diagram, it serves a purpose to visually represent the signal going from high to low. That's all it is. Students tend to have difficulty with timing diagrams. I'm not sure why, and maybe it's helpful this year that you'll have this video to keep looking back on it. But the purpose of the diagram is to look at these inputs going high and low. Just like you do in your labs, you can turn them high and low and you can make a truth table. Well, here you can figure out what the output would be. So if I were to draw the output, then I basically look at the status at any given time. So for example, here it's 0, 0. So the output is going to be a 0 because it's going through an OR gate. And then at every time something changes, so now we need to look at it here. Well, it's 1, 0, so the output is 1. Here it's 1, 1, so the output is 1. Here is 0, 1, so the output is 1. So that's the purpose of it, is to be able to look at the signal changing over time and then be able to draw the output of the signals changing over time. Why do we do this? Let me relate this to reality. Why do we do this? We do this because it's important what this output is going to look like as time changes, because there's a lot of applications where we need to know, what would happen at a certain sequence in operations. So here is the question. The question says, the waveforms A and B represent inputs to an OR gate, changing over time. Draw the waveform that represents the output. So the question here is, draw the waveform that represents the output. Now, you're all asking me, how do you know that they went from 0 to 1 and 1 back to 0? How do you know how this happened? The answer is, I made this up and I made this up. This is the question. This is the question you're given, and you're going to put the answer here. So ideally in an academic environment like yours, ideally you would, have a final exam where you would sit down and this is given and this is given, and the input waveforms, and I ask you, what are the output waveforms? So the answer is, I made this up and I chose to, make up a sequence of events where people are pushing buttons like that. That's just the question. So let's do the answer, and I'll do the answer in green. So the answer is, let's see, the question is, draw the waveform that represents the output X. Well, so the answer in green, I know it's an OR gate. So I first need to refresh my memory with what on earth an OR gate means. That means A and B went into it, and the output is X. And here's how it behaves. Wow. And here's how it behaves. So an OR gate, we should know its truth table by now, in that the output is 1 if one or the other or both are equal to 1, or else the output is 0. So now to draw the waveform, let's see what the output is. So the answer is, the output is X, and it's either going to be low or high with respect to time, the same timeline as above. So we see that some things happened. A signal changed here and here and here. And so I recommend that you draw these vertical lines where the signals change. And then in between each of those vertical lines, you need to figure out what the output would be. So it's a little bit of a puzzle. It's kind of fun. I like to look at, try to do it easy. So I'm going to look at this line of the truth table, and I'm going to say wherever A and B is 0, I'm going to use purple here. Wherever A and B are at 0, then the output X is going to be also at 0. Here's 0. So A and B are 0 in this little space, aren't they? So A and B are 0 there. So I'm going to say, well, this started at 0, but then I got a 1 and a 1. In here, one of them, B is 1. Where have I got 0 and 0 again? Oh, look at that. I'm 0 here and I'm 0 here. So in this little space, it's 0. Then it's a 1 here. It's a 1 here. It's a 0 and a 1 here. So it's looking to me like all the rest of these spaces have at least one of the inputs as a 1 or both. So this is our output. It's 1 for all the rest of the time. So I took a shortcut there. I didn't look at each segment. I could look at each segment and say, well, I have a 1 here, 1 and 0, the output is a 1, and 0 and 1, the output's a 1, and etc. I could look through there, and 1 and 1, here's where it's 1 and 1, it's 1 and 1 here. And I could draw each little segment separately, but I could be a little bit more efficient by just saying all the rest of the answers are a 1. So this is the correct answer. So this is output with respect to time. So that's how you draw a timing diagram of this particular example, where the waveforms for A and B changing over time are given in the question, and you're asked to draw the waveform output. Very, very important and practical in the real world. You can do yourself a little Google search and take a look at all the applications where waveforms are used in various instrumentation applications.